traditional electrical grids face inherent limitations rooted in their unidirectional design. Power flows from centralized generators to consumers, a model that struggles with dynamic demand, intermittent renewable sources, and isolated faults. These vulnerabilities often result in localized outages, inefficient energy utilization, and a delayed response to system anomalies. The increasing complexity of energy supply necessitates a more adaptive and resilient infrastructure. The intelligent grid, or smart grid, addresses these challenges by integrating advanced digital communication and control technologies into the existing electrical network. It transforms the power system from a passive delivery mechanism into an interactive, self-aware network. This evolution allows for two-way communication and real-time data exchange, fundamentally altering how electricity is generated, distributed, and consumed. A cornerstone of this transformation is the advanced metering infrastructure, known as AMI. Unlike traditional meters that record consumption monthly, AMI deploys smart meters capable of measuring and transmitting energy usage data in granular, near real-time intervals. These devices communicate directly with the utility, often via secure wireless or power line communication networks, eliminating the need for manual readings and enabling dynamic pricing structures. The continuous flow of data from AMI provides unprecedented grid visibility. Operators can monitor energy consumption patterns, identify peak demand periods, and detect irregularities across the distribution network. This data analytics capability informs operational decisions, allowing for more precise load forecasting and optimized power dispatch, thereby enhancing overall system efficiency. However, the sheer volume and sensitivity of data generated by AMI introduce significant challenges in data management and cybersecurity. Protecting consumer privacy and securing critical infrastructure from cyber threats becomes paramount. Implementing robust encryption, access controls, and anomaly detection systems is essential to maintain the integrity and trustworthiness of the intelligent grid's data pathways. Beyond meters, the intelligent grid incorporates a distributed network of sensors and Phasor measurement units, or PMUs. Sensors monitor parameters such as voltage, current, and temperature at various points along transmission lines and substations. PMUs provide synchronized measurements of electrical waves, offering a precise, wide-area view of grid conditions, critical for detecting system instabilities before they escalate. This pervasive sensing capability contributes directly to enhanced grid reliability and fosters self-healing properties. When a fault occurs, smart grid components can rapidly detect the location, isolate the affected section, and reroute power around the damaged area. This automatic restoration process minimizes outage duration and reduces the impact on consumers, moving beyond manual fault location and repair. Despite these advancements, the integration of diverse smart grid components from multiple vendors presents interoperability and standardization hurdles. Ensuring that different devices, software platforms, and communication protocols can seamlessly exchange information is crucial for optimal performance. Developing universal standards and open architectures is an ongoing effort to prevent system fragmentation. A critical aspect of the intelligent grid is its ability to integrate distributed energy resources, orders. These include rooftop solar photovoltaic systems, wind turbines, battery storage, and even electric vehicles. The bidirectional nature of the smart grid allows these smaller, dispersed energy sources to feed power back into the grid, shifting away from a purely centralized generation model. The seamless integration of DERs directly supports the incorporation of renewable energy and decarbonization goals. By managing the variability inherent in solar and wind power, the intelligent grid maximizes their contribution to the energy mix. It dynamically balances supply and demand, utilizing storage solutions and demand response programs to stabilize the system when renewable output fluctuates. Yet, high penetration of intermittent DERs introduces complexities in maintaining grid stability. Managing voltage fluctuations and frequency deviations caused by variable generation requires sophisticated control algorithms. Operators must accurately predict renewable output and manage energy storage to prevent instability, particularly in localized microgrids. To achieve this level of control, The intelligent grid employs advanced control and optimization systems, such as supervisory control and data acquisition, SCADA, and advanced distribution management systems, ADMS. These platforms aggregate data, execute real-time commands, and facilitate demand response programs, where consumers adjust their energy use in response to price signals or grid conditions. These systems drive significant energy efficiency improvements and enable sophisticated demand-side management. By providing consumers with detailed usage data and dynamic pricing, the intelligent grid encourages energy conservation and load shifting away from peak hours. This reduces overall energy waste and defers the need for expensive infrastructure upgrades. The widespread implementation of intelligent grid technologies faces substantial investment costs and regulatory complexities. Upgrading legacy infrastructure, deploying new sensors, and developing advanced software require considerable capital. Furthermore, establishing appropriate regulatory frameworks and market mechanisms to incentivize smart grid adoption and ensure equitable cost recovery remains a significant challenge for utilities and policymakers. The transformation of the electrical infrastructure into an intelligent grid represents a fundamental shift in energy management. It moves beyond incremental improvements, establishing a foundation for a resilient, efficient, and adaptable power system capable of supporting evolving energy demands and a diverse generation landscape.